for ME 4056, Section 3, Group 4. So the purpose of this experiment is for Bredel Inc. to characterize the mechanical properties and the four-stroke cycle of the engine model in order to create a control of the engine for optimal energy generation. So now we're going to go into some background and methods about this experiment. An internal combustion engine is a mechanism that features a piston inside of a cylinder which moves up and down twice per cycle. The cycle contains four strokes. They are intake, where air and fuel are drawn into the cylinder; compression, where the air-fuel mixture is compressed to a very high temperature and pressure; the power stroke, where the spark plug fires and the air-fuel mixture is ignited, thus pushing the piston down; and exhaust, where the piston pushes all the combusted air-fuel mixture out of the cylinder. Here is the experimental setup. It features a force transducer that measures the torque of the motor, and a Wheatstone bridge converts the torque into voltage that is read by the Elvis 3. A calibration is needed to ensure the accuracy of the readings from week to week and to get the gain and torque offset of the function. Also, the encoder wheel measures the crankshaft angular displacement. It is marked where the piston reaches top dead center, allowing for a point of reference for future measurements. During week 1, the engine head is removed and there is no air injection. Measurements are taken at 3 different speeds, 1 low, 1 medium, and 1 high, recording both the acceleration period and steady state. This is to record the engine response under these conditions and obtain relevant mechanical parameters to be used in the work kinetic energy equation. Measurements are also taken with only flywheel to measure the inertia of the flywheel. For week 2, the engine head is on, but there is still no air injection. This time, all measurements were taken at steady state, but still at a low, medium, and high speed. Additionally, measurements were taken with no flywheels attached. All of these measurements are ultimately taken in order to solve this work kinetic energy model equation. This equation states that the change in energy of the flywheel is directly related to the change in work of the system. The work of the system has been broken down into subsections in order to isolate particular aspects of the motor system. Some key differences between weeks 1 and 2 are: in week 1, since the head is off, we can assume that work of air is 0 and the work discrepancy is 0. Whereas in week 2, work of air is not 0 and is actually divided up between the power and compression strokes for the calculation.
The following slides show the calibration and data collection during the first week of the IC Engine Lab. For the calibration, 4 discs with varying masses were placed on the force transducer to get an output voltage. Multiplying each mass by gravity and the calibration arm length provides the torque value corresponding to each voltage. This process was repeated each week at the beginning of lab. These torque and voltage values were then plotted against each other, and a York regression analysis was performed on the dataset to provide the gain and offset torque values. On this plot, the red circles show the raw data points, and the dotted blue line shows the calibration equation, where torque is equal to 3.101 times the input voltage. These 3 plots show the angular position versus time for low, medium, and high RPM. The orange arrows show that the time to reach steady state increases as RPM increases, and the period of each oscillation decreases as RPM increases. These 3 plots show the total motor torque versus angular position accelerating from rest for low, medium, and high RPMs. The work equations below show that the work of the motor from A to B is equal to the sum of the average torque values times 10 degrees times pi divided by 180. The work of friction is equal to the torque due to friction times the angular displacement from A to B, and the work of the piston is equal to the negative motor work minus the work from friction at steady state. These 3 plots show the motor torque plotted against time for low, medium, and high RPMs. The steady state at each RPM is plotted in orange, while the transient state is plotted in blue. The orange rectangle underneath the curve shows the area for the steady state motor work. These 2 data tables compare the work values in steady state versus accelerating from rest from the previous slides. In both cases, the values of the motor work and the work from friction increase with RPM. The change in energy of the flywheel is shown in the equation below to be the work of air plus the work of the motor plus the work of friction plus the work of the piston plus the discrepancy of the work from A to B. However, the experimental setup without the engine head makes the work of the air 0, the work of the piston is negligible to their relatively small values, and the discrepancy of the work is also negligible. During steady state, the motor work and friction work are equal, so the change in energy of the flywheel is also zero. However, when accelerating from rest, the work of the motor is increased, so the change in energy of the flywheel is equal to the difference between the motor and the friction work. The moment of inertia of the flywheel is equal to the motor work minus the friction work divided by the angular velocity squared. The theoretical moment of inertia from the geometry of one of the plates is equal to 1/2 times the mass times the radius squared. This value is determined to be 0.005 kilograms meters squared, and having 4 of these plates as the flywheel for our experiment gives a theoretical moment of inertia of 0.02 kilograms meters squared. The low RPM had an error of 37%, the medium had an error of 156%, and the high yielded an error of 5%. The accuracy from the high RPM data is most likely due to the increased number of revolutions completed for data collection at higher speeds. It should also be noted that the actual plates are not perfect cylinders, and some have additional holes in the plates. Numeric integrations of the work are also only approximations.
After calibrating the torque sensor again for week 2, the gain had increased to 3.6 compared to week 1's gain of 3.1. This further proves the need to calibrate the system before each experiment due to unforeseen changes occurring. After calibrating the torque sensor, a work kinetic energy analysis was done by performing a numerical integration on angular position versus motor torque for low, medium, and high RPM. As expected, the work done by the motor increases as RPM is increased. Work analyses were done with no flywheels attached to understand the effect of removing the flywheel. We see that the effect of removing the flywheel results in a larger torque fluctuation and increases the work of the motor. Removal of the flywheel mass reduces the inertia, which in turn increases omega and reduces stability, which is why we see a larger torque fluctuation. Additionally, as omega increases, frictional work increases, so the work of the motor must increase to overcome the frictional work. Our updated kinetic energy model now includes the work due to air as well as the work discrepancy. The work discrepancy was calculated by subtracting the compression stroke work from the power stroke work, and was calculated to be 11.07 joules. Looking at A, B, C, and D, each stroke of one cycle can be identified in the angular position versus torque plot. As expected, angular displacement per encoder bin uncertainty remains unchanged, while the cumulative work of the motor and calibrated torque measurement uncertainty increase as flywheels are removed for low and medium RPM. This is not the case for high RPM, which is most likely the result of recording data with inconsistent RPMs, leading to lower uncertainties for the no flywheel scenario. To confirm that our sensors are adequate for this experiment, the work discrepancy should not be in the bounds of uncertainty. Given that our calculated work discrepancy was 11.07 joules, our equipment proved to be adequate.
Finally, we're going to go into some conclusions and future work. So next week, we'll perform a third calibration of the force transducer, and we will need an analysis with the engine head on and air injection to simulate combustion. We will need to optimize the work output based on the cycle phase and update the work kinetic energy model with the data from the air injection. So now some conclusions. If the engine has a large work discrepancy, that means the model is inaccurate. But if the engine has a small work discrepancy, that means the model is accurate. And in this case, since our work discrepancy is about 11.07 joules, it is relatively small compared to other work values in this system. So we will say that it is accurate in modeling the 4-stroke cycle.